Alright, so the question we're going to look at now is how to validate if a binary tree is a binary search tree. So if you recall, a binary search tree is a special type of binary tree where every element to the left of a node is smaller than it, and every element to the right of a node is greater than it. So that's the kind of properties we're going to look for when we examine the binary trees in this problem. So the first step of any problem is to fully understand what the question is asking for to make sure we're not solving for the right thing. So let's look at some example outputs and inputs that the question gives us to gain a better understanding of what we're trying to solve for here. So in the first example here, we see that the input is a binary tree with two levels. At the parent node, we have a 2, and its left child is a 1 with a right child of 3. And this output's true because everything to the right of 2 is smaller than it, since it's just the node of 1, and everything to the right of 2 is greater than it, since it's just the node of 3. So that's why we're outputting true in this case. In example 2, we have a tree with 3 different levels. At the root, we have a node of 5, and on the left side, we have a node of 1. So that's fine because 1 is smaller than 5, and that's what we expect in a binary search tree. However, on the right side, we see that there's a 4 and a 3, and both the 4 and the 3 are smaller than the 5, which invalidates the properties of a binary search tree, and that's why we're outputting false here. So the examples that the interviewers give you are going to be okay and fine. It'll help you understand the question a little bit, but it always helps me to write out some of my own examples and kind of walk through my own examples so I get a better understanding of how I want to approach the problem and eventually solve it. And sometimes when I'm coming up with my own examples, I'll be able to think about different edge cases that wasn't clear to me in the beginning, and I'll also be able to hopefully map out little subproblems in the problem itself so that I could have an easier approach to solving the problem. So let's start out by drawing some examples of our own and determining whether they would be binary search trees or not, and kind of going through our thinking process to gain a better understanding of how we should approach the problem. So the simplest base case I could think of in this case is if we had a tree with just one node. So say we have a tree of node 5. So in this case, would we return true or false? Well, since this tree has just one node, there's nothing to the left and there's nothing to the right, so there's nothing that could invalidate it as a binary search tree, so we would return true in this case. Now let's go one level deeper and build our tree. So say our tree was now 2 levels with a 5 and a 3 on the left side and a 10 on the right side. So visually, we can automatically see that this is a binary search tree because the 3 is on the left side and it's smaller than 5, and the 10 is on the right side and it's greater than 5. But it's easy to see a question and immediately come up with an answer. But what actually happened in our head to make us determine that this is a binary search tree? Well, we looked at the root node. So the root node is 5. We looked at the root node. We looked at its value. And we made sure that it's greater than the left child of the root node's value. So this is just some simple pseudocode to kind of map out our thinking process as we were processing this in our brain. And similarly, we did the same thing for the right child. So we looked at the value of the root node and we made sure that it was smaller than the right node of the root. So in pseudocode, this is kind of what was going on in our brain as we were trying to imagine how to determine if this is a binary search tree. Okay, great. So let's build this out one level further and see if we can apply the same rule that we did for this tree into a bigger tree. So let's try to build out a tree that has 3 different levels. So in this case, would you think this is a binary search tree? So take a moment to look at the picture and try to imagine whether this could be a binary search tree or if there's something that's missing from this. So after I looked at it, I think this is a valid binary search tree since everything to the left of 10 is greater than it, everything to the right of 10 is greater than it, and everything to the left of 10 is smaller than it. And similarly, everything to the left of 20 is greater than it, and everything to the right of 20 is greater than it, and everything to the right of 20 is. So let's take a look at this tree. So yeah, I think this tree would be a valid binary search tree because everything to the left of 10 is greater than it, and everything to the right. So let's take a look at this binary search tree. So we know this binary search. So let's take a look at this binary tree. So we know this binary tree is a binary search tree. So how do we kind of determine that? Well, let's build off of what we had in this previous example. So let's imagine we were just kind of looking at this little subtree up here. So we can use the same principles that we used up here, where we examined the root value and looked at its left and right child. So this by itself is a binary search tree. And now we can apply the same principles for the smaller subtrees on the bottom. So we can look at these little subtrees individually. So this little subtree individually is a binary search tree. Everything to the left of 5 is smaller than it, and everything to the right of 5 is greater than it. And similarly here, this subtree is a binary search tree as well, because everything to the left of 20 is less than it, and everything to the right of 20 is greater than it. So if we're going with this approach here, now we're kind of doing a recursive approach where we're looking at each node and checking its left and right value, and then recursively looking at the left and right subtrees to make sure that they're also binary search trees. So we would apply the same thing, and then we would recursively call these two lines on every node. But I think the problem with this is, if you noticed, if we change this number to something, say 7, this subtree by itself is still a binary search tree, but taking it as a whole, this becomes not a binary search tree because the 7 is on the right side of 10, and anything on the right side of 10 should be greater than it. So this kind of invalidates our first approach where we simply check for little subtrees. And now we have to start keeping track of values to see what range each number at a node can be. So for example, this node here cannot be anything less than 10, and at the same time it can't be anything greater than 20. So let's draw out some examples and sketch out a tree and kind of go through each level and see how the values and the ranges for the values progress as we're building out our tree. So we can start out with a root node of 10 and go from there. So as we're going from there, what possible values can be over here on the right child and over here on the left child? So any value that's over here, we definitely know it has to be greater than 10 because it's on the right side of 10. And similarly, anything here has to be less than 10 because it's on the left side of 10. So let's say this is 5, and let's say this is 30. Now let's go one level deeper and see how those values progress. So now we're on the right child of 30. So what kind of values can go here? Well, this value of being greater than 10 definitely has to carry over. But now we also have this extra constraint that it has to be greater than 30. And since anything that's greater than 30 is also greater than 10, we forget about this constraint here. And what happens over here? So in this value here, the constraint that has to be greater than 10 carries over. And now it also has a new constraint that it has to be less than 30 because it's on the left side of 30. So we see that this constraint where it has to be greater than 10 carried over, and this constraint that it has to be less than 30 is coming from its parent node. So let's make this 20, and let's make this 60. Let's go one more level deeper just to see how these values carry over. So now that we're on the right child of this node 20, we have several constraints that should carry over. So this value should definitely be greater than 10. It should also be less than 30. But now, since it's the right child of 20, it has to be greater than 20. And since anything that's greater than 20 is also greater than 10, we can kind of forget about this one. And now we have a constraint where it's greater than 30, or sorry, it's less than 30 and it's greater than 20. So we just put something like 25 here. Alright, what about this left node here? So for this left node here, the same constraints carry over. It has to be greater than 10, it has to be less than 30. Now it also has to be less than 20 because it's on the left side of this 20. So now we see that anything that's less than 20 is definitely less than 30. So we could forget about this one, kind of reduce it to just these two constraints. It has to be greater than 10, it has to be less than 20. So let's put 15 here. So what's the pattern, if there's any pattern that you see that has emerged from this? So what we're seeing here is, as we're moving down to the left, the constraint that's staying the same is the tens. So as we're moving down to the left, the minimum stays the same. It always has to be at least greater than 10. So as we're moving to the left, as we progress left, the minimum stays the same. But the maximum, what is going on with the maximum? So as we look at here, the maximum over here there was no maximum really. It just had to be greater than 10. It could be anything bigger than 10. As we move down here, however, the maximum is now 30. So this value here couldn't be anything greater than 30. So this 30 we see came from this parent node, and similarly this 20, the maximum of 20, came from this parent node. So it looks like the maximum becomes the value of its parent node. Maximum becomes value of parent node. So now we figure out what happens when we're progressing on the left side, towards the left of the binary tree. But what happens when we're progressing right? Well, for binary search trees, the special properties about them is that, if you recall, everything to the left has to be smaller than it, and everything to the right of a node has to be bigger than it. So when we think about it in that way, it kind of means that everything, so when we think about it in that way, we can think of it as whatever happens on the left side is the exact opposite of what happens on the right side. So what do I mean by that? So if we look at this case, we see that this 20, as we're progressing right, the maximum is the one that stays the same. So if you see here, 30 is carried down as we're progressing left. And similarly here, the 10, as we're progressing right, the maximum is never changing. From 10 to 30, the maximum was that there was no bound, and from 30 to 60, the maximum had no bound. The only bound we had was a minimum. So as what happened on the left is exactly the opposite of what happens on the right. So what do we mean by that? So as we go right, let's write that down so we have a clear idea of what we're trying. So let's write that down. So what do I mean by that? So let's write that down so we have a better understanding of what we're trying to articulate here. So as we progress right, the maximum is now the one that stays the same. The max value stays the same. And what about the min value? How is that being updated? So the min value is being updated by whatever its parent nodes was. So from here, when we're at node 30, the min value was, it had to be at least greater than 10. When we progressed to 60, the min value became 30. So we can formalize that by saying the min value becomes the parent's value. So now that we have these two major components in our solution kind of thought out, I think I have a pretty good idea of how to start about going with the code. So I'm going to jump into writing some code and see how our thoughts can translate into our code. So right now, we're just given a method, and our method only takes in a tree node. So I don't really want that because I want it to be able to take in like a min and max value, kind of like what we've been drawing out earlier in our drawings. So I'm going to create a helper function that also takes in a min value and a max value. So this helper function, I'm thinking, is going to be responsible for letting me know if a root in a binary tree is valid, considering that we want this tree to be a binary search tree. So when I'm doing a lot of these tree problems, I always like to start out by some base cases. So given that my first approach was to recursively look at every node, I want to think about what my base case would be. So at what point would I want to return true? So if my root was null, so this is probably better named as just node instead of root, because now we're not really passing in the root of tree specifically. They could be more just of, they could be a root of a subtree, but a node I think it would be a more appropriate name. So if our root is null, do we want to return true or do we want to return false at its place? So imagine if our root was null. I would imagine something like here. So implicitly we know that there's two null nodes here. So when we're going down our check and we've seen the 10, we've seen the 5, we check that 5 is valid, so it's not left on 10. Now we're looking at these null nodes here. We want to return true at this point, right? Because if our tree was just this 5 and this 10, that means we have a valid binary search tree. So if we go down the values far enough to the point where we reach null values, that means we eventually come to the conclusion that this subtree is a valid binary search tree. So here I'm going to return true. Now we can formalize what our thoughts here about when we progress left, the min stays the same and the max becomes a parent value. And as we progress right, the exact opposite happens. Let's try to formalize that into code. So at this point, if we're checking a node, we have min and max values already. So what we want to do is, so the node we know should be definitely greater than the minimum value, and it should definitely be smaller than the max value. So if the nodes pass both of these conditions, what should we do? Well, we don't quite want to return true here because say we're looking at this node 30 here. And say we're looking at this 60 here. So now we have a min value of 10. So say we're looking at this value 20 here. So we have a min value of 10 and a max value of 30. So, and then we see our node is 20. Now that's valid because it's greater than 10 and smaller than 30. So what do we want to do at this point? We don't want to return true specifically, because if we return true, then we're not going to check any of its subtrees. Now we're just going to be stuck. So we don't specifically want to return true here. But what we want to do is to keep going if both of these conditions are satisfied. So we want to keep checking its subtrees if both of the conditions are satisfied. So how can we go about doing that? Well, if we want to not go on when both of the conditions are not satisfied, we could change this into the opposite of what this would be. So it would be if node is less than or equal to min value, and we change the and to an or, and then if the node is greater than or equal to the max value. So this is what we don't want. So if this happens, we want to return false. So if we formalize it, if we look at a picture here to understand what's going on, so say this number here was actually 45. So 45 is greater than 10, but 45 is not less than 30. So at this point, we want to return false, because if we see a number here that invalidates our binary search tree, we shouldn't even go on and look at the rest of the numbers here. So that's why we want to return false once we see that this number does not satisfy the constraints. So as we go down here, now we check that this node is valid in the binary search tree. So now we want to look at it, recursively look at its left and right subtrees. So we want to return the nodes left. And if we go back to our drawing here, when we're recursing left, the min stays the same and the max becomes the value of the parent node. Okay, so the min stays the same and the max value becomes the value of its parent node. And similarly, we want the same thing. We also want the right subtree to be a binary search tree. So we want to call the same thing on the right subtree. But in a drawing that we figured out earlier, when we're recursing left, we want the max value to stay the same. And the min value should be updated to be the parent's value. So the min value is now the parent's value, and the max value stays the same. So in our helper function, what we're doing here is we're checking to see, as we're going down a tree, we're checking to see that each node is valid, given that we assume we're looking at a binary search tree. And if we see that this node is valid, we want to recursively look in its left and right subtrees to make sure that the whole tree is valid. And as we're going down this tree, we're updating our min and max values so that we keep track of what range a certain node can be as we're going down the tree. Okay, great. So now we have our helper function. Now we need to get things started by calling the helper function with our root node. So what would be our min and max values the first time we go through our parent node? So if we look at this 10 here, what is the min and max when we create our first node in a tree? It really can be anything, right? It could be like the smallest number, it could be the biggest number, this could literally be anything. This was just a starting point for us, and we had no min and max values. So how do we formalize that into code? We can create some variables that will help us formulate our idea that this can be any number. So the way I like to do that is with a variable that's assigned to the smallest and largest integers. So with these values, now we have a starting point. So now we're saying, when we're looking at the first node, it could literally be anything. So we have no min and max values, and we're trying to formalize that by saying this is the largest and smallest integer value that I know. So we give it to it as a starting point. Okay, great. So now I've written out a solution, and I want to check if my solution works. So I'm going to first teleport all the way up here. And then I'm going to try to draw out some trees to see how it plays out with my solution. So let's start with something easy. Let's say our tree just had 2 levels for now. This is just a 5 and a 1. What's going to happen as it goes through our code? So the first time, we're going to have the starting min and starting max, and it's going to call helper. It's going to call helper on a root, which is 5, with the min integer value and the max integer value. And as we go into helper, it's going to check to see if this node is null, which is not. And then we're going to check if this is less than min, which is not. Is it greater than max? It's also not. So we're going to return helper. We're going to recursively call helper on its left and right child. So we're going to call helper on its left child, and we call it on the left child, which is 1. The min value stays the same. The max value is now updated to 5. Similarly, there's a null node on the right child. So what happens here is that we're going to call helper on a null child with the minimum being our node's value and the maximum staying the same. So what happens when we call helper on this null child? Well, it's going to go to line 20, our line 20 here, and it's going to return true. So this returns true. What about this helper child? This helper function. So this helper function calls it on 1. So this helper function is going to check if 1 is less than or equal to min. It's not, it's greater than min. And then it's going to check if 1 is greater than or equal to 5, which is also not, so it's not going to return false. So now we're going to call the helper function on its left and right children, which are both null nodes. So just for practice, let's just fill out what would go here. So on its left null node, the min value stays the same, but the max value is now 1. And for its right child, the minimum value is now 1, and the max value stays the same, which is 5. So we carry that 5 over here. And when we finally get to these helper functions, since these are both null, we're going to evaluate the statement at line 20, and we're going to return true for both of these. So now we have returned true because we've checked that every subtree in this tree as a whole is a binary search tree. Okay, great. So it works great in this case where things are a little simpler. What about a case that doesn't work? So say our tree was a 5, and on the right side we had a 3. So similarly, we would call our helper function on 5 with the min and max values. And then from here, we would call the helper function on the null node, which is the left child. The min value stays the same, and the max value is now 5. And for the right child, we'll have 3, and the min value is now 5, and the max value stays the same. So what happens when we call the helper function on 3 with a min value of 5 and a max value of integers max? So we go to line 25, and now we're checking to see if 3 is less than or equal to 5. It is 3 is less than or equal to 5. So now what happens is we're going to return false on line 26 because this part of the statement had returned true. Okay, great. So that's exactly what we wanted. So now let's try a little more complicated example. Something that we were afraid of in the beginning. So for example, the case that we were worried about in the beginning was something like this. So if we had a 20 here, this is still valid at this point, but if we add a 7 here, this becomes invalid. So why is this not a valid binary search tree? Well, if we look at the 7 here, the 7 is on the right side of 10, and everything to the right of 10 has to be greater than it, so this is the value we're worried about. Because if we were looking at little subtrees by itself, technically this little subtree by itself is still a binary search tree, but as a whole, this tree is a binary search tree. So this is what we're going to try to see if our code can catch in this case. So let's go with this. So when we start off, we're going to call the helper function on 10 and the min and max integer values. And as we call the helper function on 10, we're going to end up calling the helper function on 20. And 3. So 20 is the right node. So the right node, when we're calling the right node, the minimum becomes the node's value and the maximum stays the same. And this becomes this. So we're going to forget about this case for now because we know this is eventually going to call helper function on 2 null nodes and return true. So we're just going to worry about this part now. So now we're on helper function of 20, 10 max. So what's going on here? So we go to line 25. So we're going to check to see if 20 is less than or equal to 10, which is not. And then we're going to check to see if it's 20 greater than or equal to max, which is not. So now we're going to call helper functions on the children of the node 20. So that's 7 and a null node. So 7 is on the left side of 20, so we're going to keep its min value, which is 10, and we're going to carry over its max value. And its max value becomes 20. And for its right child, the minimum value now is 20, and the max value is carried over. Okay, so let's see what happens in this case. So now we're calling helper function on the node 7 with a minimum of 10 and a maximum of 20. So now we're going to go to line 25 and we're going to check to see if 7 is less than or equal to 10. And it is. 7 is less than or equal to 10. So now we're going to end up returning false thanks to line 26. And that's exactly what we want. So I think the solution has been working out pretty well, so I'm pretty confident, and I'm going to go ahead and enlarge this again and submit our solution and see what happens. Compile error, cannot find variable root on line 20. Because we changed the name of this from root to null earlier, so now let's change it back to node. One more try. Tree node, line 20, tree node. Missing an equal sign. So here, can you figure out what's wrong here? So here we're actually comparing tree nodes to integer values. And we should really be comparing tree nodes values to integer values. So we were missing that. So this is interesting because I can see that this input value that failed was exactly the case that failed because this is the max value of an integer value. So I think this might help if we use a long instead. That's going to make things a little more complicated for us because the values for tree nodes were stored as ints. But we can work with it. Awesome, our solution was accepted.